TV Sreekumar, Bombay Textile, now enlighten us with their works on acrylic precursors for carbon fiber. So,
very good morning, all of you. Thank you very much, Mukesh ji, Chairman Indoor Composite, and also Dr. R.K. Singh, giving me this chance to deliver my work or the work which we are doing at the Bombay Textile Research Association. High tenacity acrylic precursors and carbon fiber and India strategy. You can see that yellow fiber, which is the precursor for carbon fiber. I hope all of you know about carbon fiber, and which is one of the most important material that is needed for composite industry, and which is something which we don't have in India. So we have to always depend on the imports. So we need to at some point become independent of these restrictions that we have. The yellow fiber which you see, that is the precursor for carbon fiber, and the black one is the carbon fiber which is made out of it. Because you know that polyester can be made by melting polyester and extrude it and do a melt spinning, and you can make a polyester fiber. Polypropylene is also same way, polyethylene also same way. But how will you make carbon fiber? You cannot dissolve carbon and convert it into a carbon fiber, or you cannot melt carbon and convert it into a carbon fiber. So the process is, you first take a precursor, the yellow fiber which you have, and then heat it to various temperatures up to 1000 degrees Celsius to convert them into carbon. Because all the polymeric material, they have carbon, hydrogen, nitrogen, and a little bit of oxygen. So you have all the carbon-carbon chain, and oxygen is or hydrogen is at the other side. Like if you take polyethylene, it is CH2, 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 CH2. So if you remove all the hydrogen by heating, so you will get carbon remaining. But the problem with polyethylene is that if you heat it, it will start melting. So it will no more be in the form of a fiber. So what you take is, one of the most important precursor for carbon fiber is acrylic fiber. Acrylic fiber is common, which is used in making sweater also. But for making carbon fiber, you need special acrylic fiber. And that special acrylic fiber is called a high strength precursor. So if the strength of the precursor is very high, the strength of carbon fiber is also going to be very good. If you compare the strength of normal acrylic fiber, which is used for sweaters, is about 3 to 4 GPD, grams per denier, in the textile terms if we talk about. But that of the precursor, carbon fiber precursor, is above 6 grams per denier, 6 to 7 grams per denier. So here, I'll be describing shortly about how we make precursor and how we can convert that into carbon fiber. And the work which we have done at the Bombay Textile Research Association with the help of the National Technical Textile Mission. And now we have that Technical Textile Mission in India. It's about 1,400 crore they are distributing. I think most of the academic institutes might have got part of it, depending on their project proposal. So we also received about 21 crore for developing carbon fiber precursor in India. As you have seen, these are the high performance fibers which are very important in the composite industry. Ultra high molecular weight polyethylene, which goes into bulletproof applications, we are importing it. Kevlar, that is again required for bulletproof, for making hard bulletproof material like helmets, and that is also being imported. And carbon fiber, which is required for all the aerospace applications. The previous presenter also has mentioned that the lightweight is very important to have a high payload. So lightweight and strength. So the strength to weight ratio is very, very important to have high payload in aerospace industry. So that is also being imported. Only glass fiber to some extent is being manufactured in India. So we need to create all these high performance fibers. So there is an opportunity in India to have all these fibers, which is very much required if we have to become a Viksit Bharat. So the properties, if you compare the properties of normal fibers with carbon fiber, what do you see? The acrylic fiber, which is the textile grade acrylic fiber, is about 0.4 gigapascal, and that is the precursor is much higher. And if you consider the T300, that is the basic carbon fiber which goes into aerospace, which has proven the airworthiness, is T300. The strength is about 3.5 gigapascal, and steel is 1.3 gigapascal. And the specific strength, if you consider, that is most important, the strength to a density, the strength divided by the density, the highest is 3.5, again for the carbon fiber, and that of steel is only 0.17. So the development of carbon fiber is very important if we have to go for a high strength, low weight structure. Carbon fiber, the area of carbon fiber where it has been made is for clean energy, energy saving, conventional energy, and high performance materials, starting from windmill to gas turbine. These days, drone is one of the things which is growing very fast. Almost 5,000 manufacturers already we have in India, and all this has to be in carbon fiber composites to have lightweighting and longer range. So very important. And India is also making in defense the Rustam UAVs, unmanned aerial vehicles. That also is mostly used with carbon fiber with different composite manufacturing technology. In conventional energies, for deep water excavation, oil excavation, it's very important because carbon fiber is something which will not have any corrosion effect, and it is used in atomic energy also and high performance materials. The word carbon fiber has grown very sharp because the industrial carbon fiber applications were used in energy, clean energy applications. So aerospace also has grown quite well, and in 2020 it was about 120,000 tons per annum of carbon fiber manufacturing has happened over the world. The economics, we can debate on this. This is something which I have considered manufacturing aerospace grade carbon fiber, because industrial grade carbon fiber is coming out much cheaper, like $20-25. If you consider like $35 per kg, then the payback is like 4 years. So you can manufacture it. So in normal case, if you have a polyester plant, the payback is 5 years plus. But if you have carbon fiber, the right kind of technology, so with 4 years is quite good kind of payback which one can expect. So the industry has to come forward and start manufacturing carbon fiber in India. So the process of making carbon fiber is that we need to have first a polymer, that is the acrylic polymer suitable for making carbon fiber. It is different from that of conventional acrylic fibers. So there is a special polymer required for carbon fiber, and we have created this technology in the Bombay Textile Research Association. And that polymer has to be filtered, then dried, pulverized, and then again you have to redissolve it in a dope tank, where you can make a honey-like structure, honey-like polymer. It's a very transparent polymer solution that is called dope. The dope is further spun through spinnerets and then converted into a precursor fiber, the precursor winder which I have shown, that the yellow fiber, and then it has to be heated at 230 to 300 degrees Celsius, then carbonized at 1200 to 1800 degrees Celsius to make carbon fiber. So it's a long process. It is not as simple as like if you make polyester, where you have polymerization, then melt spinning, winding, you got the polyester fiber. But here, polymerization itself is one process, then dope preparation, spinning, converting into the precursor fiber, then stabilization, then carbonization. So it's a process is quite a long process, but ultimately you will be getting a very nice material. So another thing which we have done is not just conventional carbon fiber. We try to incorporate carbon nanotube in it. And I hope all of you know about carbon nanotube, which is one of the strongest material where the theoretical strength of carbon nanotube is, single wall carbon nanotube is 50 gigapascal. And that of a normal carbon fiber is only 3.5 gigapascal. So what we are thinking is that if you can incorporate this carbon nanotube in the precursor level itself, that will reinforce the precursor directly. So you will have a CNT reinforced precursor, and once you carbonize it, this will give additional strength to the overall carbon fiber. Or during the carbonization process, carbon nanotube itself is a perfect carbon fiber or a nano level carbon fiber. So they will lose its own identity and the whole thing will become carbon fiber. And additionally, what we found is that during the heating process, if you see here, the change in length percentage, A is that of the pure precursor, normal precursor, while heating, B and C are precursor containing carbon nanotube. That shrinkage is much less. If you see the dimensional change here, A shrinks much faster during the heating process, but B and C doesn't shrink that much. What does it mean to the production? If it doesn't shrink during the thermo-oxidative stabilization process, you can have a higher speed, line speed, during the all precursor production process. So during the precursor production, if it shrinks, then you have to reduce the winder speed. So here you can have a higher speed during the whole precursor and also the stabilization and carbonization process. You can have a higher line speed, then you can have a higher production capacity. So you can reduce the cost of carbon fiber. So if you have a little bit of carbon nanotube in it, so the production cost will reduce further. So if you can make a carbon fiber at $15 per kg or less than $15 per kg, you can easily compete with glass fiber. So all the glass fiber you can substitute with carbon fiber if one can make carbon fiber at the cost of $12 per kg. So this is a very important thing. So what you see here, the first one, the oriented pan reinforced CNT. So the precursor containing carbon nanotube in between, that will restrict the whole polymer to shrink, and also it will stop the breakage process, where here you can see that the only pure polymer will break in between. So what we have shown here is that at Bombay Textile Research Association, we have the whole system of making the precursor, where we have that first reactor where we can make the polymer, about 40 kg, and that one polymer solution, we can convert it into in this second reactor and then do the whole spinning. I'll show, I hope this video work. Yes. So this one, the polymer is then pushed in through the coagulation bath. So you can see, I hope you can see the fibers that's coming out, the 1,000 filaments. Yeah, you can maybe show it to others. The precursor we have made. So it's about 1,000 filaments here. Sorry. So you can see this fibers that's coming out after the coagulation process. So there are about 1,000 filaments. So we have the capacity to make 1,000 filaments, 2,000 filaments, 3,000 filaments, and 4,000 filaments. So 3,000 filament is a standard industrial level of production in minimum 3K is for aerospace applications is much better. If the 3K is most expensive, then 6K, then 12K, and above 12K, 24K, and it's industrial carbon fiber. So we can make 1,000 to 3,000 and 4,000 also. So this is the coagulation bath. Now this is going to the washing baths, second coagulation and washing. And this is another washing plus stretching. It says it's a special technology. It's called the Draw Duo, and further drying and spin finish addition. And this is further stretching and collapsing of the pore porosity and also heat setting. And then it goes to the winder. So this industrial winder is in worldwide, everyone uses the same winder, sham winder, which is being used for the precursor winding. So this is how we made the precursor fiber, and we have also done some preliminary study on the carbonization process, and it is giving good kind of carbon fiber also. So we have the capacity to make 1K, 2K, 3K and 4K filaments at the Bombay Textile Research Association. This is one of the, I think, India's first this kind of a machine that which we have and the process that we have developed. Thank you. Thank you. And if you consider the properties of the precursor fiber, 6 grams per denier is the minimum requirement. So what we have is about 7.39 grams per denier. This is one of the good strength, and also 1.1 to 1.17 is the denier requirement. And these are the properties that international available precursors they have. It's about if you can see, it's about 0.12 linear density is 0.1 text, so that is equivalent to about 1.2 grams, and the tensile strength, if you see the filament numbers 3K, 6K, 12K, so we can now produce all these kind of filament diameter, denier, and also grams per denier fibers. The most important part, which I was talking about, the shrinkage part, the shrinkage reduction, which carbon nanotube is established here, and this is a work which we have done in the laboratory in a batch process by heating the both precursor fiber and the just precursor and also CNT reinforced precursor. See that the black one is the pure pan, which shrinks much faster, and the red one that is pan CNT, the right one precursor, and it doesn't shrink that easily. So this restricts, the carbon nanotubes actually restricts the shrinkage, and that is one of the most important property that we have. And the panox which we produced, the oxidized pan which we produced, have about 2.2 grams per denier. 2.2 grams per denier. You can see here 2.2 grams per denier, and that of pure pan is about 1.6 grams per denier. And this is equivalent to the internationally available panox. The panox normal strength which is available internationally, you can buy, that is about 2 GPD, grams per denier, and what we have 2.2 grams per denier after introducing some amount of carbon nanotube. So this we need to further improve the whole this process, but we can make same amount, the same kind of property in India now. So we have this technology available. So I urge all the people to collaborate with our institute so that we can make it commercial scale. With that, thank you so much. If you have any questions.
Any questions from audience?
Yes. Okay.
The basalt fiber also produce this technology.
Basalt is a melt process. Basalt is a melt process. Yeah, that is, I think, basalt is a stone-based, it's a mineral-based fiber. So that is a different process. Yes.
Can we use this precursor in type 4, type 5 cylinders manufacturing?
Yeah, once precursor is, you have to convert that into carbon fiber. Once you convert that into carbon fiber, yes, you can use in any of the, because the strength we expect, like from 6 grams per denier fiber, one can easily make T300 and even 400. So with 7.2 grams per denier, definitely we will be able to make much stronger carbon fiber. So T700 carbon fiber easily we can make. Yes, sir.
Yeah, you mentioned the process of that block flow diagram as to how to reach from pan to.
Yes, yes.
At what stage of the process is the CNT infused?
The dough preparation. During the dough preparation, yes.
You told that carbon fiber is good compared to the glass fiber, so we are speaking about can reduce up to $10, $8, so it can be comparable or can be usable for more.
Yes, yes.
But while importing CNT, so how the cost will be because it will increase. CNT is another material, so we are negotiating.
Yeah. Yeah, that's a very good question. The CNT concentration here is very, very, very less, 0.05%. So very low concentration. If you use a higher concentration, then the dispersion of the nanotube is very difficult, because then it will act as a defect size rather than reinforcing. Because at higher concentration it will not go inside it itself. So what we do is we make very small quantity, 0.05% in DMF or DMFC solution, and then that we mix with Pando. So that small quantity is enough. So that cost is less, much, much less. That you can get that advantage in the line speed directly. Because when you add carbon nanotube, all fiber becomes stronger, so you can have a higher line speed. Both in precursor spinning and also while making the panox also. So the overall speed of production is much high, so that advantage nullifies the cost of very small amount of carbon nanotube. Yes, sir.
Sir, this 0.05% is based on like optimization of the cost, or is it a sort of kinetic study which has been done to arrive at that 0.05%?
Okay, what we have done is we have done even 0.0121%. So what we found is a 0.05 is the much easy and getting the without compromising the strength of the precursor fiber.
That it will be working.
Yes.
Is there any effect of molecular weight of the precursor pan on the effect of the strength of the carbon fiber after carbonization?
Yeah, absolutely, yes, yes. So
Is there any effect of means what is the typical molecular weight of the precursor pan for this particular material?
yes. So we normally measure the intrinsic viscosity. So the intrinsic viscosity about 1.6 to 1.8 grams per DL per gram, deciliter per gram, is the most ideal. For that 1.6 to 1.8 deciliter per gram is equivalent to about 1.3 to 1.6 lakhs molecular weight.
Which solvent we are using for that particular viscosity measurement?
Pardon, sir?
In which solvent we are
DMF. So all these studies, all the solution viscosity studies are done in DMF.